So good morning, everyone. So today I'm going to be talking to you about some of the analysis we've done of looking at areas of high interest within the South Polar region of the Moon, in particular an area, the Leibniz Plateau, for ESA's Prospect instrument. And the work I'm going to present to you today is on behalf of the Prospect team, many of whom are in the room and also listed here on the slide. So just to start with, a few points. The Leibniz Plateau is an area of high elevation, and this means that because of the topography in the region, there's really good illumination conditions, and therefore this makes it a suitable area for doing mission operations and also an ideal potential landing site. And this has been identified in the previous literature, such as studies from Lemon et al. 2014. The area also has conditions for water ice and other volatiles, and this makes it a really interesting area for Prospect to land at. One of the other points is that Viper, the mission we heard about yesterday, is also landing in near proximity to the Leibniz Plateau. And therefore, these two instruments, both Prospect and Viper, if they were to be successful and land within a similar area, they could provide regional contacts about the water ice and volatiles within the region. One of the things we've also done within this work is produce a morphological map of the area. And what we've studied and what we found is that the morphology varies a lot across the region, from smooth with areas of very few craters and much smaller craters to the terrain being quite rough and with much larger craters and much more varied sizes. So just as a refresher, we heard from Dave this morning and yesterday about Prospect, but just as a reminder, Prospect is one of the ESA instruments on board the NASA CLIPS CP22 mission, and Prospect is designed to sample the lunar subsurface, and in particular, it's designed to sample water ice and volatiles and create a volatile inventory. So it's made of two components, both ProSeed, the drill, which will sample the lunar surface down to 1 meter's depth, and also ProSolar, which will analyze these samples. And the key thing for Prospect, which I'm going to be talking to you about today, is we want to go to an area where volatiles such as water ice can be expected. And that's what we're going to be focusing on. So for any kind of mission landing site analysis, there's several kind of constraints to consider. And these are a few of the ones that we followed. So we wanted to land within the South Polar region, studying from 84 degrees south and poleward, so going towards the South Pole. And we assumed it was best to avoid landing within the Artemis 3 candidate sites. Additionally, we wanted to meet the requirements of Prospect, specifically the scientific requirements, so looking for areas that are thermally stable for water ice and other volatiles. And really importantly, we want to make sure that we're landing in a safe area. So typically for missions, we say around 10-degree slopes is kind of a safe condition. So we followed that. And we also wanted to make sure that there was no hazards or as minimal hazards as possible. And we define this as anything bigger than 5 meters in diameter, such as craters and boulders. We assumed a landing ellipse of 100 meters. And for this particular presentation, I'm focusing on purely the science requirements for Prospect, and we are not considering any of the CP22 level requirements or any of the needs of the other payloads on CP22. So how did we do this? We use remote sensing and ArcGIS software ArcPro with a various range of different data sets to analyze the Leibniz Plateau, which, as I mentioned, has previously been identified as an area of interest. And we ourselves, as the Prospect team, we also independently analysed this area and identified it as an area of high interest for Prospect during our own down selection studies. We've used high-resolution digital elevation models to analyse the topography and the slopes present, and we've also used NAC images to observe the textures and roughness present across the region and make a morphological map of the area. We've also produced some illumination models, and this is using an independent model at a spatial resolution of 5 meters and a temporal resolution of 1 hour. And we've also done thermal models also at the spatial resolution of 5 meters. So the Leibniz Plateau, you can see here an image of the elevation across the South Polar region with Shackleton crater at 90 degrees south at the center and expanding outwards to around 84, 85 degrees. And hopefully you can see that in red is the areas of high elevation, so typically those plateaus and those massifs, and then the areas in blue is areas where there's craters and basins, much lower areas of elevation. And looking in detail on the kind of smaller zoomed in area, we can see that there is high elevation, showing that there's areas of better illumination than average, which would make it an ideal place to do mission operations and landing in this area. And one of the other things about this region is there's many craters across the plateau, and therefore these craters provide some PSRs, some larger ones because of the larger craters present, but also some micro PSRs and cold traps, and therefore these colder temperatures increase the likelihood of us finding volatiles such as water ice. As I mentioned, one of the key things about this area is the Viper mission is landing on the Nobel crater. And therefore, if these two missions were successful, then we'd be able to provide much greater regional context about the water ice and volatiles present in this region. So zooming in now, and the area that we kind of down selected as an area of high interest is located here in the little blue box. You might not be able to see that, but it's towards the top middle section. And zooming in then, we have a NAC image mosaic showing what this area looks like. And hopefully you can see that the illumination conditions, we see those much larger PSRs, as well as the areas that are illuminated in those kind of grey, whitish colours. So you can see the conditions present within the area of interest. So looking at the topography, this is a 1 meter elevation map on the right-hand side here, or your left, I think. And in this 1 meter digital elevation, you can see again in red the areas of high elevation and in blue the areas of much lower elevation. And hopefully what you can see is we pick up much higher details, such as those much smaller craters, and allowing us to do much more detailed analysis of the area. We also produced a slope map from the digital elevation model, and hopefully what you can see is that the colours are mostly those white, cream yellow colours, which are slopes of less than 10 degrees, and therefore making it an area suitable for future missions to land in. So moving on to the morphological map we've created, we were using NAC images to observe the textures and roughness within the region, and we came up with 4 morphological units. We had a smooth unit where there was very few craters, and any craters that were present were typically small, up to about 10 meters in diameter. We then had an undulating unit where there was still few craters, maximum size was around 15 meters in diameter. We also had a rough, less textured unit where there was more variation and many more craters within this unit, typically getting up to around 20 meters in diameter. And the rough textured unit where there was many craters and more variation in sizes, up to 20 meters and bigger sometimes. And also there were some boulders present in some areas. So this is what the morphological map looks like, and hopefully what you can see from these different colours present in is that the morphology varies a lot across the area of interest. We have the green showing the smooth areas, and then blue, kind of blue-purple showing the undulating textures, and then the yellow and pink showing those much rougher areas. And this has implications for the roughness and therefore potentially the illumination conditions and the thermal conditions at that very small, high detailed scale. So moving on to the illumination and earth visibility analysis, Maris Ring has produced an independent model for us at the 5 meter scale. And hopefully what you can see is that the area is very illuminated. So this is really good for carrying out future mission operations in the area. And what you can see towards the bottom right of the illumination map is there is this PSR. And so this would be an area that would need to be avoided for landing, but however does provide colder conditions and colder temperatures to the surrounding region. And again, you see the same pattern in the earth visibility map. And here you can see that there's good earth visibility across the area. But again, in that PSR, the earth visibility is not as suitable. And these two maps are done at the surface, so 0 meters elevation. But if we also look at 1 meter observations, so this would be a kind of approximate height of a solar panel on any future missions, you can see that both the illumination and the earth visibility conditions improve. So you can see that most of the area, apart from that PSR, is showing really good illumination, making it an ideal place to land if you had that 1 meter solar panel height. And also the earth visibility is also improved as well, except for that PSR region that I mentioned. So linking to that, the thermal analysis, Tris Warren produced an independent thermal model for us, again at that 5-meter resolution. And you can see that the kind of illumination conditions and the thermal analysis is somewhat linked in that the areas where we had, okay, thank you, the areas where we had good illumination. So if we go back to the kind of top right of this illumination map, you can see the same area is showing higher temperatures, so typically up to about 225 degrees Kelvin. And then what we did is we took this temperature map and assumed that water ice could be a temperature that would be for where water ice could occur would be at 110 degrees Kelvin. And so we produced a water ice depth map. And what you can see, the areas where there's the higher temperature and the higher illumination conditions in the light blue, so towards the top right of the water depth map, is where we would not expect water ice to exist at any depth. But however, the darker regions where that PSR is and just above the PSR, there are temperatures that are cold enough and therefore water ice can be expected at the surface and within the shallow subsurface down to 1 meter. And so these would be areas, those dark blue colors would be the perfect areas for us to send Prospect to if we were to land in this region, as we can expect to be able to sample water ice from those areas and other volatiles. So just to summarize, some future work that we're going to be continuing working on, there's still much more to do, is to continue doing that thermal analysis, particularly that 5-meter scale and also 1-meter resolution, going into a bit more detail. Also doing illumination analysis, continue with that, but looking specifically for areas that are colder and darker at the surface, but are illuminated at that 1-meter height or other solar panel heights. And also looking for comparisons between the Viper landing site and the Leibniz Plateau area and how we can build on that regional context between these different missions. And with that, I'll take any questions. Thank you. Over here.
Go to the back first.
Oh, yeah, sorry.
Okay. Can I go first? Okay.
Yeah, please do.
Thank you very much. Just a question. In the frame of the commercial launches and so the CLIPS one, how much the payloads, for example, in this case, Prospect, can affect the choice of the landing site? Thank you.
So I've only been involved with Prospect in this particular mission, so I don't have experience on other examples. We were involved within the CP22 landing site selection and the whole process, and we've been part of the team in that. And so for us, we've been involved and had those discussions. I can't speak for other experiences. I think it would be on a case-by-case basis and would vary depending on the mission. But for us, we have been involved, yes.
So this seems like a very involved process with lots of data and lots of data evaluation, but there are common themes for landing and requirements for landing. Can you envision that this is something that maybe gets automated in the future or becomes a little easier to do to somehow, if we're going to go back to the moon a lot, hopefully, can we make this process easier?
Yes, absolutely. I think there's been a lot of things that we can learn from the landing site studies that both the Prospect team have done and also other teams have done. We now have some areas that are continually popping up in the literature as areas of interest for either volatiles or geologically interesting. So I think we're starting to kind of build up across the community a kind of database, if you like, of sites that would be of interest, and that then future studies and future missions could kind of go straight to those studies and start to use those as those starting points rather than kind of doing a whole overview of the whole South Polar region, a whole equatorial region. I did actually recently see that there are some groups that are starting to use more machine learning in their approaches to kind of automatically kind of identify sites a bit more and inputting the data sets into an algorithm and then kind of feeding it certain parameters, such as saying slopes of less than 10 degrees, or this is the area of interest we're looking at. So I think it's something that will start to pop up more and more across the literature. Yeah, I did see a study the other day that was doing exactly what you just mentioned. It was very much in the early stages and wasn't for a particular mission, but was more testing the method out. But I'd be really excited to see how this could evolve with time.
Yes, Brian Day from NASA Survey. I'd just like to point out that NASA's Moontrek data visualization and analysis portal includes a number of tools for landing site analysis and traverse planning, including AI and ML-based crater detection, boulder detection, slope analysis, lighting analysis, and line of sight communications planning, taking into account local topography. And those tools are all available to you online. Also, we have a pipeline for generating NAC mosaics and DEMS.
Great. Thank you very much for pointing that out, Brian. Check one.